My friends, welcome back to my YouTube channel. In this class, I am going to discuss some PYQs, that is previous year GATE questions, which are based upon the concept of cyclic heat engine. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. The first question that I am going to discuss is that was asked in GATE 2012 XC. You see, the question was like this: consider two Carnot heat engines A and B operating in series. A receives heat from a reservoir at 1750 Kelvin and rejects heat to another reservoir at temperature T. So first Carnot heat engine operates between these two temperature limits. One is higher temperature 1750 Kelvin and the lower temperature is T, capital T. Engine B receives an amount of energy same as that rejected by engine A from the reservoir at temperature A. The basic concepts of Carnot heat engines operating in series means when the amount of energy rejected by one engine becomes the energy supplied to another engine, then only those two engines are said to be working in series. So here whatever energy is rejected or whatever heat is rejected by engine A, the same is supplied to engine B, and that temperature is the common temperature is the temperature T. This is the common temperature. Engine B then rejects heat to another reservoir at 320 Kelvin. 320 Kelvin is the lowest temperature in this two series of Carnot heat engines. If the thermal efficiencies of both the engines are the same, if the thermal efficiencies of both the engines are the same, then the temperature T is approximately, out of these four given options, we have to find out the correct option. So, suppose this is the temperature from which 1750 Kelvin, this is the high temperature from which engine A receives heat. Engine A receives heat. Suppose this is engine A. Clockwise, heat engine is always a work producing machine. So let this heat supplied to this engine A is Q1 and Q2 is the heat rejected by engine A, and that is rejected at a temperature. Suppose this temperature is T, temperature T. This is written in the question that A receives heat from a reservoir at 1750 Kelvin and rejects heat to another reservoir at temperature T. So, this engine A receives energy or heat from this temperature and rejects heat to this temperature. Then, whatever energy is rejected by engine A goes to engine B. You see, just go through this line. Engine B receives an amount of energy same as that rejected by engine A from the reservoir at temperature T. So, energy rejected to the temperature T by engine A will be the energy supplied to the engine B from this temperature T. Suppose this is Q2 is the energy rejected by engine A to the low temperature T, then that Q2 is also the heat supplied to engine B. This is the concept behind engines operating in series. So that means Q2 is the energy rejected by engine A at low temperature T, and this low temperature T becomes the high temperature for the engine B, and the amount remains same. So Q2 here, Q2 is rejected to temperature T, and that Q2 is absorbed by engine B from the same temperature T. And the lowest temperature is, of course, suppose this is Q3 and this temperature is given to be 320 Kelvin. Engine B then rejects heat to another reservoir at 320 Kelvin. 320 Kelvin. So this temperature is nothing but 320 Kelvin. And we have already discussed that suppose this is the work output of engine A and this is work output of engine B. And we have already discussed that when two Carnot heat engines are operating in series, and if their thermal efficiencies are same, if their efficiency, suppose if efficiency of A equal to efficiency of B, then this intermediate temperature, this is the intermediate temperature, will be the geometric mean of these two extreme temperatures. If efficiency of A equal to efficiency of B, only when these two engines, Carnot heat engines A and B are operating in series. Series means whatever energy is rejected by engine A, that becomes the heat supplied to engine B. Then only they can be called to be in working in series. So when these two Carnot efficiencies of these two Carnot heat engines are same, when they are operating in series, then the intermediate temperature is nothing but the geometric mean of two extreme temperature. One is 1750 and another is 320 Kelvin. So obviously 1750 multiplied by 320 geometric mean. So this becomes 748.33 Kelvin. So the correct answer will be the option B. Option B, 748 Kelvin. You see, if in this question it would have been given that the work output of these two engines are same, if WA had been equal to WB, then this intermediate temperature would have been the arithmetic mean of these two temperatures. जब efficiency equal होता है तो intermediate temperature, this is the intermediate temperature, becomes the geometric mean of two extreme temperatures, which are in this case 1750 Kelvin and 320 Kelvin. And if in place of this efficiency, if it had been written that the work output of these two engines are same, then the intermediate temperature would be 1750 plus 320, that is arithmetic mean of these two temperatures. But in this case, it is given that the efficiency of engine A is equal to efficiency of engine B. So that's why the intermediate temperature will be nothing but the geometric mean of two extreme temperatures, that is square root of product of these two temperatures, 1750 multiplied by 320. So answer would be 748 Kelvin and option B would be the correct answer. This was asked in the GATE 2012 XC. So question number 2, it was asked in GATE 29-2009 XC. And the question is like this: a heat engine E1 operates between an infinite reservoir at 800 degrees Celsius and a body B. So engine E1 operates between an infinite reservoir, that is at 800 degrees Celsius, and a body B. The temperature of the body B remains constant at 550 degrees Celsius. Heat transferred to the engine E1 is 900 kilojoule. That is heat supplied to engine E1, and the work output is 200 kilojoule. So out of the heat supplied 900 kilojoule, engine E1 produces a work output of 200 kilojoule. Another engine E2 operates between body B and a temperature at 27 degrees Celsius. So engine E2 operates between body B and temperature at 27 degrees Celsius. Heat rejected to the atmosphere is 350 kilojoule. Heat rejected to the atmosphere is 350 kilojoule. The thermal efficiency of the engine E2 is out of these four options: 0.39, 0.5, 0.61 and 0.635. So you see, engine E1 operates between 800 degrees Celsius. Engine E1 operates between 800 degrees Celsius. First of all, we will convert this into Kelvin. So 800 plus 273, that is 1073 Kelvin. 1073 Kelvin. Let heat extracted by this engine A is Q1. This is engine E1. So Q1 is given to be 900 kilojoule. This is given. Heat transfer to the engine E1 is 900 kilojoule and the work output is 200 kilojoule. So work produced by this engine is 200 kilojoule. And engine E1 operates between this temperature 800 degrees Celsius and a body B. So this is body B. This is in fact the difference between, this is a infinite heat reservoir, thermal energy reservoir, means whatever amount of heat you extract from it, its temperature will not decrease. And if you add any heat to it, its temperature will not also increase. But this is a finite body, and if you supply heat to it, its temperature will increase. But another important line is there. You see, and a body B, the temperature of the body B remains constant at 550 degrees Celsius. 550 degrees Celsius. How is this possible? So 550, by converting this into Kelvin, this becomes 550 plus 273, that is 823 Kelvin. But it is, the important line is, the temperature of body B remains constant. How is this possible? How is this possible? This is possible only if whatever amount of heat is supplied to this, the same amount will be rejected by this body. Only then only the temperature will remain constant. Temperature will remain constant at 823 Kelvin. See, this is 900 kilojoule and this is 200 kilojoule. That means the Q2 will be 900 minus 200, that is 700 kilojoule. Because according to the principle of energy balance, when a system completes a cyclic process, summation of energy transfer across the system boundary is 0, or summation of total energy entering into system during the cycle is equal to summation of energy leaving the system during that cyclic process. So total amount of energy that enters into system is 900, that exits is 200 plus Q2. Obviously 900 is equal to 200 plus Q2, which implies Q2 is equal to 700 kilojoule. And since the temperature of body B remains constant, that is written in the question, temperature of body B remains constant. That means same amount of heat is also rejected by body B. So that same 700 kilojoule has to be rejected by body B. Then only the temperature of body B will remain constant. So this is the engine E2. So again it produces heat rejected to the atmosphere is given. Heat rejected to the atmosphere, which is at 27 degrees Celsius or 300 Kelvin. Suppose this is, atmosphere is 300 Kelvin. So heat rejected to the atmosphere is 350 kilojoule, that is given. That means this heat is given to be 350 kilojoule. So this is an heat engine, and to which 700 kilojoule of heat is supplied, and it rejects 350 kilojoule. Obviously the work produced by this engine is W2 will be this minus this minus this. This is the total energy entering into system during the cyclic process, and these two energies are leaving because the arrow is away from the system. These two are energies leaving the system. So 700 is equal to W2 plus 350. That means W2 will be 700 minus 350, that is 350 kilojoule. So efficiency you are required to find out the thermal efficiency of the engine E2. So net work output efficiency of engine E2 will be net work output divided by heat supply. This is the definition of efficiency. What fraction of heat supplied is converted into net work output? In this case, net work output is 350 kilojoule and heat supplied is 700 kilojoule. So that is 0.5. 0.5. So answer will be option B, 0.5. The thermal efficiency of the engine E2 you are required to find out, and you can say that in this case E1 and E2 are also working in series because the energy rejected by engine E1 is same as the energy supplied to engine E2. Next question is question number 3. You see, a heat engine produces power of 1 lakh kilowatt. Heat engine produces a power of 1 lakh kilowatt. The heat engine operates between 800 Kelvin and 300 Kelvin. It has a thermal efficiency equal to 50% of that of Carnot engine for the same temperatures. That means this is not a case of reversible heat engine because its efficiency is 50% of that of Carnot heat engine. The rate at which heat is absorbed from hot reservoir. The rate at which heat is absorbed from hot reservoir is required to be found out from the given options. 1 lakh kilowatt, 1,60,000 kilowatt, 2 lakh kilowatt, 3,20,000 kilowatt. This was asked in GATE 2003 chemical engineering. So you see, heat engine works between 800 Kelvin and 300 Kelvin. So this is high temperature is 800 Kelvin and low temperature is 300 Kelvin. So, and heat engine produces power of 1 lakh kilowatt. So this heat engine produces, suppose this is Q dot H is the heat supplied to this heat engine, and Q dot L is the heat rejected to the low temperature reservoir, and this is the work produced. So you see, and this is given, this is 1 lakh kilowatt rate of power produced. This is given in the question. You see, 1 lakh kilowatt. So, and efficiency is given to be, this efficiency of heat engine is given to be 0.5 of efficiency of Carnot heat engine operating between these two temperature limits. You know, maximum efficiency is always that of Carnot heat engine operating between given two temperature levels, and the efficiency of this particular heat engine is nothing but the 50% of that of Carnot engine. So we have to calculate the efficiency first. So this is equal to 0.5 multiplied by 1 minus efficiency of Carnot heat engine is nothing but, in this case it is 1 minus 300 divided by 800 is equal to 0.5 multiplied by 5 by 8. This becomes 5 by 8. So this is equal to 5 by 16. So efficiency of this particular heat engine is 5 by 16. But we are required to find out rate at which heat is absorbed from hot reservoir. That is Q dot H we have to find out. W dot we have already, it is given. So efficiency is nothing but, efficiency is nothing but W dot divided by heat supplied, Q dot H, that is equal to 1 lakh divided by Q dot H, and this is already we have calculated, it is 5 by 16. So now this is the equation we have to solve. 1 lakh kilowatt divided by Q dot H is equal to 5 by 16. 5 by 16 is the efficiency we have calculated from the given data. But we have to find out Q dot H. What is the energy absorbed by the heat engine from this? So Q dot H becomes multiplied by 16 divided by 5, and this becomes 3,20,000 kilowatt. 3,20,000 kilowatt. So option D is the correct answer. Option D is the correct answer. 3,20,000 kilowatt. So question 4, it is proposed that the solar energy be used to heat a large collector plate. This is like this. You see, solar energy be used to heat a large collector plate. The energy in turn be transferred as heat to a fluid within a heat engine, and the engine would reject energy as heat to atmosphere. So here the sink is atmosphere. Experiments indicate that 0.5 kilowatt per meter square of energy can be collected at the operating temperature of the plate, and the maximum efficiency of heat engine, that is the efficiency of reversible heat engine between given temperature levels, is 0.2. The maximum efficiency in this case is 20%. The minimum collector area that would be required for a plant to produce 1 kilowatt of useful shaft power. So what is the area of collector required to produce 1 kilowatt of useful shaft power? Options are 1 meter square, 10 meter square, 100 meter square, 1000 meter square. So it was asked in the GATE 2008 XC. So you see, here is the collector. Here is the collector plate at a given temperature. Suppose this is T1 temperature. This is the collector, and from sun, suppose solar light is falling on this collector plate. You see, solar energy be used to heat a large collector plate. The energy in turn is transferred as heat to a fluid within a heat engine. So, and the energy that is falling, or heat that is falling on this collector plate is at this rate, that is 0.5 kilowatt per meter square, where A is the area of this collector plate. Area of the collector plate. Per meter square में इतना energy falls on the collector plate, and the collector plate is at temperature T1. So and again in turn whatever energy falls upon this collector plate, that energy goes to heat engine, and again that is some amount of heat is rejected to sink, that is suppose temperature is T2. This is T2 is atmosphere, nothing but atmosphere. So this is the heat engine working between these T1 and T2 temperatures, and let say minimum area पूछा है, the minimum collector area that would be required for a plant to produce 1 kilowatt of useful shaft power. Suppose W dot is 1 kilowatt given. 1 किलोवाट शाफ्ट पावर प्रोड्यूस करने के लिए कितना एरिया चाहिए कलेक्टर का, मतलब कितना हीट चाहिए, यहाँ से हम निकाल सकते हैं व्हाट वुड बी द एरिया. व्हाट इज द हीट सप्लाइड टू द हीट इंजन, फर्स्ट वी हैव टू कैलकुलेट, then only we can calculate the collector area. So per unit area this amount of energy is absorbed by this collector plate. Let you see, let A be the collector area. Let A be the collector area. Collector area in meter square. So total amount of energy, amount of heat or energy absorbed by plate, absorbed by collector will be 0.5 A kilowatt, because the rate of heat that is falling on this collector plate is 0.5 kilowatt per meter square. If the area of the collector plate is A, then what would be the total amount of heat absorbed by the collector? That is 0.5 A. So this heat suppose is 0.5 A. If this collector plate absorbs 0.5 A amount of heat, then that is also supplied to this heat engine. 0.5 A is the amount of heat that is the heat supplied to this heat engine, and 0.5 A is the energy that falls on the collector plate, or the energy that is absorbed by collector plate, and that energy again is going to the heat engine as heat supply, and that is 0.5 A. So you see efficiency is equal to, you know that the formula is efficiency is equal to W dot divided by, this is Q dot H, you can say this is the Q dot H, that is heat absorbed from the high temperature reservoir, Q dot H. So W dot divided by Q dot H. In this case W dot is fixed, because you are required to find out what is the collector area, minimum collector area required for producing 1 kilowatt of shaft power, that is W dot divided by that is 0.5 A. 0.5 A. This W dot is fixed because it is given 1 kilowatt shaft power produce करने के लिए कितना एरिया चाहिए, minimum collector area. That line is important. You see the minimum collector area, the minimum collector area. So from this equation you see efficiency is equal to W dot divided by 0.5 A. So area would be minimum when this is maximum. From this relation what we can conclude is, because since it is fixed, W dot is fixed at 1 kilowatt, हमको 1 kilowatt shaft power produce करना है, and that is fixed. So if this is constant, then this will be minimum collector area पूछा है, so this will be minimum, A will be minimum only when this is maximum. So I can write efficiency is maximum. Efficiency maximum is equal to W dot divided by 0.5 A minimum. So A minimum is what is required to find out required to be found out. You know, maximum efficiency is again given, that is the maximum efficiency of heat engine, that is the efficiency of reversible heat engine operating between these two temperature level, and that is given to be 0.2. So that means 0.2 is equal to 1 kilowatt divided by 0.5 From this equation, we can easily calculate minimum area required is 1 divided by 0.2 multiplied by 0.5 meter square. That is equal to 0.1. This is equal to 10 meter square. So minimum collector area required to produce 1 kilowatt of shaft power, 1 kilowatt of shaft power would be 10 meter square, and minimum collector area is required only when the efficiency is maximum, from this equation only. So the correct answer would be option B, 10 meter square. So next question is like this: a reversible heat engine in a satellite operates between a hot reservoir at temperature T1 and a radiating panel at temperature T2. So reversible heat engine obviously operates between two temperatures. One is higher temperature, that is T1, and lower temperature is T2, and lower temperature is a radiating panel from which certain radiation takes place. Heat is transferred through the mode of radiation. Radiation from the panel is proportional to area A and T2 to the power 4. T2 to the power 4. The constant of proportionality is Stephen-Boltzmann constant sigma. The ratio of the work output W to the temperature difference T1 minus T2 is, out of these four options, you have to find out the correct option, and it was asked in GATE 2008 XC. You see, this is suppose the higher temperature is T1, and which is obviously going to remain constant no matter whatever amount of heat you extract from it, because this is a reservoir. Suppose the temperature heat absorbed from this hot reservoir is Q dot H, and a reversible heat engine is operating between these two temperature limits, reversible heat engine, and suppose this is Q dot L, and rate of work produced is W dot, and this low temperature reservoir is suppose T2, and this energy that is emitted, that is rejected to this low temperature reservoir, is also transferred through the mode of radiation. And suppose this Q dot L is whatever amount of energy is absorbed by this low temperature reservoir, that is again emitted by radiation, and that radiation is directly proportional to sigma, that is directly proportional to area of this panel, and its temperature raised to the power 4. So obviously it is equal to, since it is proportional to Q dot L is proportional to area and again T2 to the power 4, so I can write Q dot L is equal to a constant, and that constant is Stephen-Boltzmann constant sigma, and A T to the power 4. So Q dot L is nothing but sigma A T to the power 4, where sigma is Stephen-Boltzmann constant. You see, this is a case of reversible heat engine. So according to thermodynamic temperature scale, you see thermodynamic temperature scale, Q dot H divided by TH equal to Q dot L divided by TL. And this is applicable for reversible heat engine or reversible refrigerator, this scale. This is thermodynamic temperature scale, and in this case Q dot H by TH in place of TH I can write this is T1 and this is T2, low temperature. High temperature is T1 obviously and low temperature is T2. So Q dot H divided by T1 is equal to Q dot L divided by T2. From this, Q dot H is equal to Q dot L multiplied by T1 divided by T2. You see, Q dot L is nothing but sigma A T to the power 4. So that I can write. So this is equal to sigma A T2 to the power 4 multiplied by T1 divided by T2 is equal to sigma A T2 to the power 3 multiplied by T1. This is Q dot H. Q dot H. What is W? W dot is nothing but, you see, according to the principle of energy balance, W dot is nothing but Q dot H minus Q dot L. So Q dot H minus Q dot L. So this is equal to, in place of Q dot H, I can write this one. Sigma A T2 to the power 3 T1 minus sigma A T2 to the power 4. And this is equal to sigma A T to the power 3 taking common. This is T1 minus T2. T1 minus T2. So from this I can find out the ratio W dot, which is required to be found out. W dot divided by T1 minus T2 is nothing but sigma A T2 to the power 3. T2 to the power 3. This is required to be found out. You see, the question is the ratio of work output. In fact, this is rate of work output. This is W dot. If this is W, there is no problem in that, and I will take this in the simple form, not in rate form. This is W, rate of work output. If it had been expressed in terms of power, then dot would have been placed in every term. So now, since it is given in terms of energy, so it would be QH, and everywhere certain changes have to be made. QH by T1 is equal to, so this is QL. QH by T1 equal to QL by T2, because it is expressed in terms of energy, not in terms of power. So there is no problem in that. From that, but the question is, you see, the ratio of work output W to the temperature difference T1 minus T2. W divided by T1 minus T2. This is W divided by T1 minus T2 is nothing but sigma, Stephen Boltzmann constant, multiplied by A multiplied by T2 to the power 3. So the correct answer would be option C. Option C. Option C would be the correct answer. That's all. Thanks for watching.